Equilibrium constant we use the symbol Kc for any equilibrium constant. All right, so Kc is an equilibrium constant, and it can be written for two types of equilibriums. So first we'll have to figure out what two types of equilibriums can exist. Two types of equilibriums. The first type of equilibrium that can exist is known as a homogeneous equilibrium. And the second type is the heterogeneous equilibrium. What does homo mean? Homo means same. And what does hetero mean? It means different. Now, what is the thing that is different in between both of them? That's the state or phase of our reactants and products. All right. So in homogeneous equilibrium, all the reactants, for example, A plus B goes into C plus D. This reaction is at dynamic equilibrium. Now, this dynamic equilibrium would be a homogeneous dynamic equilibrium if everything that is present is in the same phase or state. All right. So when all the reactants or everything, you can just write everything, all the reactants and products are in the same state or phase. So for instance, if this was homogeneous equilibrium, all of them can be gaseous. If all the reactants and the products are gaseous, what does that mean? What kind of an equilibrium this is? It would be a homogeneous equilibrium, right? If all of them are liquid, then what kind of an equilibrium would this be? This would be
Homogeneous.
a homogeneous equilibrium. If all of them are, some are liquid and some are aqueous, for example, like this. Now the states are not same, but all of them, we can say that they are, it's happening in water, for example. It's happening inside a liquid, right? So aqueous is a phase. It's basically being dissolved in water, right? So liquid and aqueous is the same phase. You can say that they're both the same phase. They're not the same state, but they're kind of the same phase. All right. So if all of the reactants are inside water, for example, one reactant can be liquid and the other can be aqueous, but they're in the same phase. They're inside water. That means they're in the same phase. That means they are homogeneous to each other. All right. So this would be a homogeneous equilibrium. So what do we want on both sides? We want the same states or same phase on both sides. All right. And in heterogeneous equilibria, what's the difference between homogeneous and heterogeneous? In heterogeneous equilibria, in the reaction, you would have different states or phases on both sides. All right. Or more than one state or phase on both sides. Clear? So when all the reactants and products are not in the same state or phase. So for example, your reactants were gaseous and your product is liquid. That would be different, right? So that would be a heterogeneous equilibrium. Are you clear?
Yep.
A reaction involving solids and liquids, both. That's different states. So that would be a heterogeneous equilibrium. A reaction involving solids and gases, that would be heterogeneous equilibrium. A reaction involving everything in gas, that's a homogeneous equilibrium. Everything is present in the same solution, or everything is aqueous, that's again homogeneous equilibrium. But for heterogeneous equilibrium, you'll find more than one state. All right. Now we'll move on to the equilibrium constant. Now remember that for any reaction that is reversible, for any reversible reaction, we can write the expression for equilibrium constant. Wherever equilibrium is involved, you can write the equilibrium constant or the expression for the equilibrium constant. Now, what does the equilibrium constant do? Now, in irreversible reactions, you do not need any equilibrium constant because they do not reach equilibrium. And it's very easy to make ratios because we know that the two reactants, for example, will react 100% and convert into the product, right? And the molar ratios are used in order to find out how much product you'll find here and how much product you'll find, for example, for D. That's because the reaction completes 100%. So you can make ratios on the left-hand side or on the right-hand side. It's very easy. You can make the ratios of the products with the reactants in order to find out how much product is going to be made because 100% of the reaction is happening. All of the reactants are converting into product, right? So we could make ratios over here. But in reversible reactions, this is not possible. In reversible reactions, the reaction never completes. Right? The reaction is never completing. So what we cannot do is we cannot make ratios from the left-hand side. It's not like if you use 1 mole of A, you'll get 1 mole of C. That's not true. That's only true in irreversible reactions where 1 mole of A will definitely convert into 1 mole of C, right? Because the reaction completes 100%. But in irreversible reactions, but in reversible reactions, this 1 mole of A, some of it will convert into product, some of it remains as A. Why? Because at equilibrium, you'll find both things. Is that clear?
Yep.
So since all of the reactants do not react over here, or the reaction does not complete 100%, we can say that this is a partial reaction, right? Some of it reacts, some of the products are made, some of the products are going back into reactants, so the reactants are not consumed fully. So we cannot make ratios with the left-hand side. Cannot make ratio or stoichiometric ratio with the left-hand side. But there is a need to figure out how much product will be made if for example, if a reaction goes to equilibrium. So in order to quantify that, or in order to quantify reversible reactions, just like we quantify irreversible reactions, which is very easy, you just make ratios simply. In order to quantify reversible reactions or equilibrium reactions, which do not 100% complete, so it is not possible for us to make ratios and figure out how much product will be formed. So we had to form a way or quantify this equilibrium in a way so that we're able to find out how much product is supposed to be formed and how much reactants are supposed to be left at equilibrium. All right. So it's basically a way of quantifying equilibrium. Are you clear?
Yep.
So that's where the equilibrium constant comes in. So for any equilibrium, you can write down the equilibrium constant. All right. And that equilibrium constant is basically telling you how much product will be formed or how much reactants will be consumed in this case, because you cannot directly make the ratio in these equations. Because we know that the 100% reaction does not take place like in irreversible reactions. So for reversible reactions, we needed to make a way in order to find out the specific concentrations of each reactant and each product at equilibrium. Clear? So let's take an example. For example, SO2, it's a reaction in the contact process that 2 moles of SO2 react with O2 gas, for example, and form 2 moles of SO3 gas. Now it is completely correct that 2 moles of SO2 and 1 mole of O2 would not make 2 moles of SO3. All right. If I put 2 moles of this and 1 mole of this, I'm pretty sure, I'm 100% sure that all of these moles will not convert into product over here of the reactants, right? Some of them convert into product, so we cannot make a ratio. So if the ratio is 2:2, that does not mean if you use 2 moles of this, you'll get 2 moles of this. No, this reaction is at equilibrium. So out of these 2 moles, maybe 1 mole reacts completely to give you 1 mole of this. But the other 1 mole remains unreacted at the equilibrium. It remains over there as the concentration of the reactant that is left at equilibrium. All right. So what do? We make a Kc expression. So equilibrium constant Kc comes over here. So the first concept is how to write the expression of Kc for equilibrium constant. So in order to write the expression for equilibrium constant, what you need to do is, I'll give you an example. So this was an example of a reaction which comes to equilibrium and how we cannot apply the ratios directly over here because the reaction does not go to 100% completion. All right. So how to write the equilibrium expression or Kc expression? This is the first thing. So for that, I'll take a general example. For example, if you have A and B reacting to give you C and D, and this reaction is at dynamic equilibrium. All right. So A has, for example, let's say A moles of A. The small a represents the molar coefficient or moles of A. All right. A moles of A react with B, small b moles of B, and gives you C moles of C and D moles of D. The small letters are the equilibrium, are the molar coefficients over here. All right. Now, in order to write the Kc expression, what do? First, remember that whenever you're writing the Kc expression, Kc will always be equal to the concentration of the right-hand side, whatever is on the right-hand side, divided by the concentration of whatever is on the left-hand side. This is the general form. All right. So concentrations of the species on the right-hand side divided by the concentration of the species on the left-hand side. And since it is an equilibrium expression, always insert the concentrations of the right or left side species which are present at equilibrium. The equilibrium concentrations must be inserted over here. All right. So let's make the expression now. So Kc would be equal to what's on the right-hand side? You have C and you have D, right? So concentration of C, square brackets represent concentration. I'm just going to label this after that. Multiplied by the concentration of product D divided by the concentration of the left-hand side, which is reactant A, into the concentration of reactant B. Are we clear up till here? So
Yep.
the right-hand side over left-hand side. All right. Now, the first thing you need to remember is that square brackets represent a very special unit of concentration, that is mole per dm³. So any square bracket over here means mole per dm³. All right, that's a concentrations unit that are represented by square brackets. So square brackets are very important in Kc expression because you insert concentrations in the expression. All right. Now the second thing, whatever the molar coefficient over here with these reactants and products, it's going to become the exponent or power of that reactant or product in the Kc expression. You get what I'm saying? So
Yeah.
C had how many moles of C? Small c moles, right? The small c
Yeah.
becomes over here the power of the product C, of the concentration of product C. All right. Same goes for D. The small d becomes the molar coefficient of D, becomes the power of D in the Kc expression. And the small a, which is the molar coefficient of A, that becomes the power of concentration of A in the Kc expression. And the small b, that becomes the power of the concentration of B in the Kc expression. Is that clear?
Yep.
Now, the next thing, since Kc is a equilibrium constant, remember that the only concentrations that you'll insert over here should be which concentrations? The initial, the final, or the concentrations of CDAB at equilibrium, if you're calculating the equilibrium constant.
Them at equilibrium.
Yep. These must be the concentrations at equilibrium. Are we clear?
Yep.
And what's another thing that is very important? These concentrations that you're writing over here, which are present at equilibrium, they must be in which unit? Mole
Moles
per
per
dm
dm.
cube. If they're not in mole per dm cube, you cannot insert them over here, because the square bracket is telling you exactly which unit the concentrations must be in order to insert them in the Kc expression. Are we clear?
Yep.
All right. So what happens is that we allow this reaction to happen. And once this reaction reaches equilibrium, so initially, for example, you had 100 moles of this and 100 molecules of this. Let's say that this was initial. Now the reaction starts happening. Some C and D start forming. So, and initially you had 0 molecules of this and 0 molecules of this. Now the reaction started happening. Some C and D were formed, and then the reaction finally reached equilibrium. So at equilibrium, you had 50 of this, 50 of this, and you got 50 of this and 50 of this. Which of these concentrations should I be inserting in the Kc expression in order to find the equilibrium constants value or the Kc value? The equilibrium ones or the initial ones?
The equilibrium.
Yep, the equilibrium ones, right? And I need to make sure that they are not in any other unit except for mole per dm cube. All right. Once they're all in mole per dm cube, you can now insert them in Kc expression and then solve for the value of Kc. Are we clear?
Yep.
All right. Now there's an important thing that you need to consider over here that is related to homogeneous and heterogeneous equilibria. Remember that in homogeneous equilibria, you do not have to worry about which substance you have to write and which substance you don't have to write, because in homogeneous equilibria, either all of them will be in gaseous state or all of them will be in the same solution. That means they will be in the same phase or in the same state, always in homogeneous equilibria. All right. But in heterogeneous equilibria, if you have a heterogeneous equilibria, for which I will give you an example later. If you have heterogeneous equilibria, remember that we never mention any solids in the Kc expression. All right. We never mention
Yep.
any solids in the Kc expression. So I'll just write that as an important point, that never mention solids in the Kc expression. Only gases, liquids, aqueous states are mentioned. All right. Only gases, liquid, or aqueous state. And whenever the gases, liquid, and aqueous states are present, it will most probably be a homogeneous equilibrium if they are present on the both sides. But for example, even in heterogeneous equilibria, if one side is gaseous and the other is liquid, still you write all of them, right? But if you find a solid on either side, you do not mention it in the Kc expression. Are we clear?
Yep.
So now we know how to write the Kc expression. We write the products the right hand side and we divide them by the reactants, which is the left hand side, right? And whatever the molar coefficient is present over here, the small letters that I've written, that will become the power of concentration in the Kc expression. So now let's do the example that we've written before. So let's say write down the expression for Kc for the example that is 2 moles of SO2 gaseous plus O2 gas goes into 2 moles of SO3 gas. Now, in order to write down the Kc expression, what should I do? I'll write Kc is equal to, what is it equal to? Right hand side over left hand side. So what's present on the right hand side? It is SO3, right? So the concentration of SO3, what should be the power of SO3? The molar coefficient is 2. So SO3 to the power 2 divided by what's present on the left hand side. There's SO2 and there's O2 gas, right? So now what should be the power of SO2? It's 2 moles. So power 2, and this is 1 mole, so power 1. The molar coefficients become the power. Are we clear?
Yep.
All right. So let's write another example, then we'll move towards finding the unit of Kc. Now, Kc is the digital value that you're going to calculate. The equilibrium constant, it is a digital value that you need to calculate. All right. So let's do another example. For example, you have a reaction, let's say an esterification reaction, for example. You have CH3, COOH. By the way, what's the type of equilibrium over here in the first example, this one?
It's the homogeneous
Yeah,
one, right?
it's a homogeneous equilibrium. So CH3, COOH liquid plus CH3, CH2OH liquid goes into CH3, COO, C2H5 liquid plus H2O liquid. Now this reaction is at equilibrium. I need to write the equilibrium constant for this, the expression for equilibrium constant. This is a balanced equation. So this is 1 mole, this is 1 mole, this is 1 mole, and this is also 1 mole. It is balanced. Now I need to write the equilibrium constant. So how do I write Kc expression? I write Kc would be equal to the right-hand side over the left-hand side. What's present on the right-hand side? There's the ester CH3, COO, C2H5. Its concentration to the power, what? 1. And then water, H2O to the power 1. And on the left-hand side, we have the carboxylic acid, CH3, COOH to the power 1 into this alcohol, which is CH3, CH2OH, and its power will also be 1. This is how you write the equilibrium constant. Is that clear?
Yep.
So let's do one more example, and after that, I'll give you, or I'll teach you how to find the units over here. So let's do the Haber's process. C, that is N2 plus 3H2 goes into 2NH3 gas. All of them are gaseous, so it's a homogeneous equilibrium. So in order to write the Kc expression or equilibrium constants expression for this equilibrium, what will you do? You'll do Kc is equal to the right-hand side, which is NH3. Its concentration to the power 2, because 2 is the molar coefficient, divided by left-hand side, there's N2 to the power what? 1, and H2 to the power what? 3. Because the molar coefficient is 3. That becomes the exponent or the power of the concentration brackets. Are we clear?
Yep.
Now, I'll give you a difficult example after this, in which you have to keep the note in mind that you never mention solids, but you mention everything else. All right. So now let's move on to how to, first we learned about how to write the expression. Now let's find out how to find the units of Kc. How do I find the units of Kc? So let's take the first example, the first expression that I wrote, and then write down the units that are present over here. Now, in order to find the units of Kc, whatever units of Kc will be left over here, what you need to do is you need to figure out what units are present over here. Now, do remember, what does a square bracket mean? The unit is mole per dm cube. One square bracket represents mole per dm cube, right? So how many mole per dm cubes do I have on the upper side? Yep.
2.
I have 2 times mole per dm cube, right? So mole per dm cube into mole per dm cube on the upper side. And how many mole per dm cubes do I have on the lower side? I have
2.
3. So mole per dm
Oh,
cube,
yep. 3.
2 these ones and 1 this one, right? So mole per dm cube, mole per dm cube, and mole per dm cube. So how many of these cancel out with each other? This cancels out with this. This one cancels out with this. So I'm left with what? I'm left with 1 over mole per dm cube, right? Now, this is never the final unit of Kc. You always need to bring the units into the numerator in order to find the correct unit. All right, never leave the units like this. You always need to bring the units up to the numerator to find what the real unit is. All right, so Kc units right now are 1 over mole per dm cube, which will finally be what? Mole power 1. When you move it into the numerator, what would the power become? -1. Right? It's an indices rule that whenever you take an inverse of a power, it becomes negative. All
Yep.
right. And dm minus 3 would become dm plus 3. So this would be the unit of Kc. Now it's very hectic to write mole per dm cube so many times. So what you need to do is you can do it like this also. Or just write the square brackets. Now you know that one square bracket represents mole per dm cube, right? So just write two square brackets on the top. So 1 times square bracket and 2 times because it's a square. And then how many square brackets on this lower side? You have 3. So this square bracket will cancel out with this cancels out with this. Now replace the unit. It becomes 1 over a square bracket, right? And square bracket represents what? Mole per dm cube. The unit of mole per dm cube. And then move it into the numerator. That will become mole minus 1 and dm plus 3. Right? So this is the shortcut. Instead of wasting time writing mole per dm cube so many times, you can just do it with the square brackets. Are we clear?
Yep.
So the unit of Kc over here is what? So the Kc unit would be whatever the value of Kc. I'll just assume that it's X right now. The unit of Kc would be mole minus 1 and dm cube. All right.
Yep.
Let's take the second example of this. So duplicate. Let's take this example now. Now in this example, what are the units of Kc? So Kc has 2 square brackets on the top and 2 square brackets on the bottom side. So now these square brackets, what do they end up doing? They end up canceling each other out. So in this case, does Kc have any unit?
No.
It has no unit, so you need to mention that in the answer. That this Kc value has no unit. All right? Now
Okay.
remember this note. If the moles of reactant are equal to the moles of product in the equation, Kc will have no units because their square brackets cancel out with each other. Now you see that the reactants had how many moles in this example? How many moles of reactants are present in the equation? There's 1 mole of the carboxylic acid, 1 mole of the alcohol, right?
Yep.
The 2 moles of reactants and how many moles of products? 1
2.
mole of the ester and 1 mole of water, so 2 moles. So their moles are equal. That is why the Kc had no units, because their square brackets then in the end cancel out with each other. So it's just a note. If you remember that, you'll never need to calculate. You just write no units because the moles of reactants and products were equal. They will always cancel out. Are we clear?
Yep.
And the last example, in which the Haber's process example, in this we'll have to find the units again. So let's do that. If I do it for this example, then the units of Kc must be what? You have 2 square brackets on the top, and you have how many? 4 on the bottom side. So 1 and 3, three are these. So now what happens? These 2 cancel out the 2 at the bottom, and you're left with Kc is equal to 1 over mole per dm cube into mole per dm cube. So can I write this as Kc is equal to 1 over square of the bracket?
Yep.
Right? So now I just replace mole per dm cube over here. So 1 over the square of mole per dm cube. Square. Now this square is for the mole and this square is also for the dm cube. So Kc becomes what? It becomes 1 over mole into square is mole square, and dm minus 3 into 2 is -6. Right? This multiplies with the 1 over here and the 3 over here. All right. So that becomes Dm minus 6. Now the final unit of Kc, what should that be? Mole would go up and become -2, and Dm minus 6 would go up in the numerator and become +6. Are we clear?
Yep.
So this is how you find the unit of Kc. All right. So you need to know how to write the expression, and then you need to know how to write the unit of Kc. Are we clear?
Yep.
Now let's take an example where a solid is also mentioned at equilibrium. So that would be writing Kc for heterogeneous equilibria. For example, you have H2O gas reacting with carbon solid or red hot carbon, and it produces H2 gas and carbon monoxide gas. Now this reaction is at dynamic equilibrium. But what type of equilibrium is this? This is a heterogeneous equilibrium, right? Because the states or the phases of the reactants and products are not the same. They're different. Is that clear?
Yep.
The carbon is over here in solid and all the other things are in gaseous state. So more than one phase is present. So this is a heterogeneous equilibria. Now, in order to write the Kc expression, what am I going to leave out?
The solid.
Yeah, I'm going to leave out the solid and I'm going to write it for all of the other things that are present. Is that clear?
Yep.
So the important difference in homogeneous and heterogeneous equilibria is that we will never include any solids in the Kc expression. Clear? So if I write the Kc expression for this and then try to calculate the unit, so that would be Kc is equal to right hand side, that's H2 to the power 1, and then the right hand side, that is carbon monoxide gas to the power 1 divided by, should I write carbon solid in this expression?
No.
No,
You
I'll
should.
only write what on the left hand side? Only H2O to the power what? 1 again. The molar coefficient of this is 1, this is 1, this is 1, and this is 1. Whatever the molar coefficient, that becomes the power of concentration in the Kc expression. Now, what would be the unit of Kc? So unit would be, so you have 2 mole per dm cube brackets on the top, 1 mole per dm cube bracket on the bottom. So this one cancels out with this one. So you're just left with unit of Kc, that is a single bracket in the numerator. So what should be the unit? That would be mole per dm cube. All right. So in this case, the unit is mole per dm cube. Are we clear?
Yep.
So what if you had ions? Another example of heterogeneous equilibrium, that would be copper 2 plus aqueous ion, copper solid reacting with Ag1 plus aqueous ions and forming copper 2 plus aqueous ions and Ag solid. I need to balance this equation. This would be 2 and this would also be 2. Now, if I want to write the equilibrium expression for this, how would I write that? So Kc would be right hand side over left hand side. But what do I leave out over here? The solids on either side, right? So right hand side would be the concentration of copper 2 plus to the power what? The molar coefficient over here is 1. So to the power 1 divided by, on the left hand side, what do I leave out?
The solid.
Yeah, the copper solid. So I just write Ag1 plus concentration on the left hand side to the power what? 2. Because that's the molar coefficient of Ag ion over there. Are we clear?
Yep.
So let's do one more example. And that is, for example, calcium carbonate's decomposition. So calcium carbonate solid would decompose and form calcium oxide, solid plus carbon dioxide gas. Now I need to write the Kc expression for this. So if I want to write the Kc expression, that would be right hand side over left hand side. But what do I mention from the right hand side only? The carbon dioxide gas.
Yep.
I leave out the solid from the right hand side. And from the left hand side, what do I write over here? Do I write the calcium carbonate solid over here?
No.
No. So the Kc expression would only be this. Are we clear?
Yep.
Now you know how to write the Kc expression, what to not write into the Kc expression, what the square brackets represent over here, that's the unit of mole per dm cube, and how do you calculate the unit of Kc. All right.
Yep.
So this was all about Kc. Now what we're only left with is so the question says a mixture of 2.5 moles of H2 gas and 2.5 moles of I2 gas was allowed to reach equilibrium. The equilibrium mixture, contained 4 moles of HI, hydrogen iodide gas. Calculate Kc. Now it says to calculate Kc. Now, first of all, I need to give you the equation. So this reaction is between H2 and I2, and they both react together to form HI gas. All right. And if I balance this equation, 1 mole of this, 1 mole of this, and 2 moles of HI, this balances the equation. So this reaction, what happens in this reaction, there's initially you put in the reactants. All right. So you put in 2.5 moles of H2 and 2.5 moles of I2. You close the container, they start reacting, and then they reach equilibrium. And then when you reach equilibrium, at equilibrium, the equilibrium mixture contained 4 moles of HI gaseous also. All right. So what you need to do is, in order to do the calculations, always remember, whenever you're asked a question of Kc, we want to make this table that I'm going to make right now. So I'm going to make a table over here that's going to have the headings initial moles at the start of the reaction, and then how many moles were used, and then how many moles would be present at equilibrium. All right, these 3 headings always in the Kc question. Now, what are the initial moles of H2 and I2 that I put inside the container, or that were allowed to react with each other?
2.5.
Yep, 2.4. So I had 2.4 moles of this, and I had, 2.5 moles of this, and I had 2.5 moles of this, right? How many moles would I have initially of HI gaseous when the reaction has not even started yet?
4 moles.
No. Initially, I would not have any HI. For instance,
Oh,
if you
yes.
had this
Yeah.
container, you just put in 2.5 moles of this and 2.5 moles of this. How many moles of HI are present right now? No moles, 0,
None.
right? It
Yep.
hasn't even been formed yet. So initially, the product over here is 0 moles. Now, what does it say? It says that they were allowed to react with each other and then reach equilibrium. Now, we do know that some of the reactants from here will be reacted or used, and some of I2 will be used, and they'll both be reacting together to form some moles of HI, right? But we cannot make a direct ratio. Why? Because we cannot say that this is 1 mole. So if and this gives you double of HI, right? That's 2 moles. So it's 1:2. So if I use 2.5 moles of this, I should get 5 moles of this. That's not true, because this reaction does not complete 100%, right? This is an equilibrium reaction. All of the reactants do not react over here. Some reactants will convert into product. How much of that will convert into product? You can never tell that directly. All right. So you need the Kc expression in order to do that. But before doing anything, you need to figure out how many moles of each of these species, the reactants and the product, must be present at equilibrium, because the equilibrium moles are the only moles that we can actually insert in the Kc expression. Are we clear?
Yep.
So you know the initial moles of H2, you know the initial moles of I2, you know that Hi initially was 0. Now the question says that the equilibrium mixture, when the reaction had reached equilibrium, this equilibrium mixture at equilibrium contained 4 moles of what? Hi gaseous, right? So at equilibrium, I have how many moles of Hi? I have 4 moles of Hi that were formed at equilibrium, right? Now, where did these 4 moles of Hi come from? By the reaction of these two. Is that true?
Yep.
These must have formed after the H2 and I2 had reacted with each other, right? So now we need to figure out how much H2 and I2 had reacted from the other side. So I do know that initially this was 0 moles Hi, right? How many moles must be formed over here of the product so that I end up with 4 moles at equilibrium? Yes.
So 4 moles
4
have to
moles.
be used?
That means 4 moles of Hi were formed, right?
Yep.
So at the end, I got 4 moles at equilibrium by adding the initial and the produced moles of Hi, right? These were the moles produced. Who will produce these moles? H2
The
and I2,
reactants.
right?
Yep.
H2 and I2. So now I can make the ratio over here. Now I can see that this much H2 was produced. So how much I2 or H2 should be reacting from the other side? How
2
much
and 2.
H2 or I2 should be used from the other side? So now I look at the ratio. Now I can use the ratio because I have the formed moles of Hi. If I want 4 moles to be formed over here, and the equation says if 2 moles were formed, how many moles would be used from this side?
1.
Half that, right?
Yep.
1 mole. So if I have 4 moles over here, how many moles of I2 were actually used?
2.
2 moles. So I'll write minus 2 moles. These were the moles used, and this is plus because these were the moles formed of the product. All right.
Yep.
So minus 2 of this, and how many moles of H2 would be used from the other side?
2.
That would also be 2. So 2 moles of H2 were used. Now, if they were initially 2.5, 2 moles were used in making product. How many are left when the reaction had reached equilibrium?
1.
Nah, you had initially 2.5. You've used 2 moles to make product. How much are you left with? Just
Oh,
go
yeah,
upside down.
0.5,
So
but as a
0.5
total,
moles are left over
1.
here, and 0.5 moles of I2 are left,
Yep.
right? Now, there's one more thing you need to confirm before writing these equilibrium moles into the Kc expression. What we needed to do was calculate the Kc. So what I'll do is write the Kc expression. Let's write the Kc expression. Kc would be equal to what? It would be equal to right hand side over left hand side. So you have Hi on the right hand side. So Hi to the power what? 2.
2.
And H2 to the power 1 and I2 to the power 1. Now, in order to find the value of Kc, I need to insert the equilibrium concentrations over here, right?
Yep.
But now try to understand what's concentration. It's the amount of moles that are present per dm cube of volume, right? In
Yep.
1 dm cube, whatever the moles are in 1 dm cube, that is the concentration. That's the standard concentration, right? So if I tell you that this reaction was being conducted in a volume of 1 dm cube, this H2, I2 were reacting and producing HI in this 1 dm cube of volume, will all these moles be present in 1 dm cube? Yep. Are all these present in 1 dm cube?
I'm a bit confused because of the one that it's supposed to
The
be.
container
Moles per
is of
dm
1
cube.
dm cube volume,
Yeah.
right? And gases occupy the complete volume of a container.
Yeah.
So whatever the moles of H2, whatever the moles of I2, whatever the moles of HI, they're all be going to be present in this whole volume, right? That is
Yep.
1 dm cube. And the moles I have to insert over here, the unit is mole per dm cube, right? The
Yep.
square bracket means that. So mole per dm cube means you have to insert those moles over here, which are present in 1 dm
dm
cube of water,
cubed.
right?
Okay.
So that's what I'm saying, that are these moles present in 1 dm cube of volume?
Yep.
Yes, because the container was of 1 dm cube. If it were a solution, then the solution must be of the solution that is used over here must be of 1 dm cube totally. All right. So can I say these are the moles that are present of H2? Can I write them as mole per dm cube?
Yep.
Because the whole volume is dm cube. So mole per dm cube. Now can I insert them in Kc expression?
Yep.
So Kc would be, what are the moles of Hi? Right hand side, 4 moles. The square, because the expression says so, right? And then H2 moles and I2 moles. The moles of H2 are 0.5 mole per dm cube, and the moles of I2 are 0.5 moles per dm cube, and both of them have a power of 1. What should be the value of Kc over here?
64.
Are you sure? It's 4 square divided by 0.5 into 0.5.
Yep, that's what I did.
Exactly 64.
Yep.
So now I have the value of Kc, but I also need to mention the unit of Kc.
So
So
yeah.
should I calculate that?
No, it's moles per dm cubed, right?
No, you need to calculate the unit. So you have 2 square brackets on the top, that's mole per dm cube into mole per dm cube, and 2 square
Yep.
brackets at the bottom, mole per dm cube into mole per dm cube. This mole per dm cube cancels out with this cancels out with this, so you're left with no unit.
Okay.
Kc will have no unit in this case. The unit of a 1 square bracket is what? Mole per
Mole
dm,
per dm cubed.
right? You
Yep.
have how many square brackets? You'll have to see what unit remains at the end for Kc. You'll always
Okay.
have to calculate that. But you could also apply the shortcut that since the moles of the reactants and the moles of the product are equal, you will never have units of Kc.
Okay.
Right? So this was the first type of question that can be asked about Kc, in which what you're given is initial moles of the reactants and the equilibrium moles of the product. And from those equilibrium moles, you have to see how many moles were actually produced. And in order to produce those, how many must be used from the reactant side. To find out
Yep.
the equilibrium moles of all of the things, once you have the equilibrium moles, always ask yourself, are these moles in 1 dm cube of volume? If they are, you can directly insert them in the Kc expression. If they're not, then you have to convert first.
Okay.
Are you clear? So the
Yep.
next question we can do over here now would be,
What would be like an example of it not being in 1 dm cubed?
yeah, we will do that example. Yes.
Okay. And then we just have to convert it, basically?
Yes.
Okay.
You'll have to convert first because the Kc expression has square brackets, right? So that the
Yep.
square brackets mean that the unit must be in mole per dm cube, or these must be the moles that are in 1 dm cube in order to insert them in the square bracket. All right.
Okay.
Now let's do another question. Question says 0.5 moles of X2 and 0.5 moles of, let's say, Y2. These are basically diatomic reactants and or products, was allowed to react, let's say was allowed was allowed to react 0.6 moles of XY were found to be present at equilibrium. Were found to be present at equilibrium. It says to find, it's a very similar question, the value of Kc. And the equation is x2 reacts with y2 to give you 2xy. Now, what should be my first thing that I should be doing over here? I should be making the table, right? So the table includes what values of the initial mole, then the used, and then the equilibrium moles. What I'm interested in is the equilibrium moles. Those are going to help me to find out the Kc value, because in the Kc expression, you need to insert the equilibrium moles. I'm going to change one thing over here. And that would be, in the end, I'll change the volume so that we know what to do when the volume is different. All right, so let's talk about the initial moles. How many initial moles of X2? We've been given the initial moles. So 0.5 moles of X2, 0.5 moles of Y2 were allowed to react. So 0.5 moles, 0.5 moles. And what are the initial moles of 2XY right now? Yep. What are the initial moles of XY? They're 0.
Yep.
Right? Because by the reaction of X2 and Y2, you'll produce XY. So there's 0 right now. Right? So now, next thing, what is given in the question? You've been given that after the reaction reaches equilibrium, you found out that 0.6 moles of XY were found to be present at equilibrium. So the equilibrium moles of XY are given that are 0.6. Right? So now you need to see what was the change of moles, or what were the moles used of the reactants. So I'll do what? I'll say that if there was 0 over here and 0.6 were present at equilibrium, that means how many moles of the product were formed actually over here? 0.6 moles, right? These 0.6 moles were formed by the reaction of X2 and Y2. Is that clear up till now?
Yep.
So in order to produce 0.6 moles, how many moles of Y2 and how many moles of X2 must be reacting from the other side? So now we know from the equation that if 2 moles of this are produced, then 1 mole of this reacts. That means half of Y2 reacts and half of that of X2 reacts, right? So if I have produced 0.6 moles, then half of those moles would be reacting for Y2 over there, right? So these are the reacted moles. So minus how many moles? 0.3 moles react from here, right? And also of X2, 0.3 moles will be reacting from this side. Clear?
Yep.
So now I can find out the equilibrium moles. If I had 0.5 initially and 0.3 reacted, how many am I left with? 0.2 moles, right? And what about X2? I'm left with 0.2 moles at equilibrium. So at equilibrium, I have these moles of each reactant and each product. Are we clear?
Yep.
So I'll add one more thing. The volume of the container is 500 cm cube, not a dm cube. So now I ask myself, can I insert this in Kc expression? So first I'll write the Kc expression. Kc would be equal to xy to the power 2, right hand side, divided by the left hand side, which is x2, and y2 to the power 1. Right? Now I see square brackets. I see that the moles that I'll be inserting here must be present in a dm cube of volume. But what was the volume of my container in which this reaction was being conducted? That was 500 cm cube. So all of these moles will be present in how much volume? All of these moles are present in 500 cm cube.
500 cm cube.
So can I insert them in the Kc expression?
No, you have to
I
convert
cannot.
them.
I have to convert them into those moles which must be present in 1 dm cube or 1000 cm cube of solution or container. All right.
Yep.
So I need to find out those moles of XY that would be present if the container was 1000 cm cube. Those moles of Y2 or X2 that would be present if this container was of 1000 cm cube, right? So I'll make a ratio. You can either make a ratio or you can do it with the concentration formula, all right? So the ratio would be, if I have 0.2 moles in 500 cm cube, how many moles would I have of the same substance if the volume of the container was 1 dm cube, which is equal to 1000 cm cube, right? Is that clear?
Yeah. Yes.
So that
Yeah.
would be how much? That would be 0.2 into 1000 divided by 500. Yep.
Sorry, my calculator is just being weird. Divided by 500 is 0.4.
This would be how many moles?
0.4.
0.4 moles, right? Now, these are the moles that will be present in 1000 cm cube, right? That means 1 dm cube. So can I write them as the moles present in 1 dm cube or per dm cube?
Yep.
Yeah. So now I have the moles in 1 dm cube, right? And the same goes for the other one. That will also be 0.4 mole per dm cube. But the third one, the product side, you'll have to do it again. So 0.6 is present in 500 cm cube. How many will be present in 1 dm cube? That is 1000 cm cube. How many moles?
I'm getting 1.2.
Yep. So 1.2 moles would be present in 1000 cm cube. So I can write that as 1.2 moles per dm cube. Right? So now
Yep.
can I insert these in the Kc expression? I can, right? I've
Yes.
converted them. So now Kc would be equal to the right hand side, which is 1.2 mole per dm cube, square of that, and the left hand side, which is 0.4 to the power 1 and 0.4 to the power 1. What would be the value of Kc?
I'm getting
1.2
9.
square divided by 0.4 into 0.4.
I'm getting
9.
9.
All right.
Yep.
So we have 9. And what would be the units of Kc? We'll
Moles
have to
per diem.
calculate
Oh,
that.
we have to calculate
We'll
it.
have
Yeah.
to calculate that. And in order to calculate that, how many square brackets do I have on the top? 2. How many do I have on the bottom? 2. All of them cancel out with each other. So I'm left with no unit. Are we clear?
Yep.
All right. So this was one type of question. The second type of question I want to do with you is, let's do a very straightforward question in which all of the equilibrium moles are already given in the question, right? So this was one of the tough type of questions in which you're given the initial moles, you're given the equilibrium moles of the product, and then you have to make ratio in order to find out if the equilibrium moles are this, how much moles of product were made, and how many reactants must be used from the other side in order to produce those moles. And then you find the equilibrium moles of each of the substance. Then you see if they're in 1 dm cube. If they're not in 1 dm cube, you convert them in 1 dm cube, and then you insert them in Kc expression to find the value of Kc. All right. So let's label them as type 1 questions. Let's say questions type 1, in which initial mole of reactant and equilibrium moles of product are given. And then you have to make all the ratios in order to find out how many moles will be used, how many will be left at the end for the reactant at equilibrium, and how many moles of the product are present at the equilibrium. Are we clear with this type of question?
Yep.
Now let's do another type of question. And that is very straightforward. So type 2 would be equilibrium moles of reactants and products are given in the question. So you don't need to find the equilibrium moles. You're already given the equilibrium moles in the question. All right. So let's do an example of that. So FAQ would be, this is again a past paper question. So the question would be, for example, 2HI gas goes into H2 plus I2. 1 mole of H2, 1 mole of I2. All right, this is our question. The first part of the question says, write an expression for the equilibrium constant. Write an expression for Kc. So can I write the expression for Kc? What would that
Yep.
be? Right hand side, which is H2 in this case to the power 1 and I2 to the power 1 again. Right? And on the left hand side, I have HI. So I'll write HI to the power 2. Right? This is the expression. Now in the second part, it says at 120 degrees Celsius. At 120 degrees Celsius, the equilibrium mixture contains 1.47 mole per dm cube of HI gases, 0.274 mole per dm cube of each of H2 and I2. What does that mean? Of each of H2 and I2, that you have 0.274 moles per dm cube of H2 and 0.274 moles of I2, both of them, right? And the question says, calculate the value of Kc at 120 degrees Celsius. Now remember that any equilibrium constant that you have is dependent on temperature, right? Do you remember that temperature was a factor that affected equilibrium?
Yep.
You did that yesterday in Le Chatelier's principle. So remember that equilibrium constant is dependent on temperature. We'll write this over here. So you know that. Remember that Kc is an equilibrium constant and it's only changed by temperature. The value of Kc, it's supposed to be what? Equilibrium constant, right? It needs to remain constant as long as the temperature is constant. If you change the temperature, then you'll change the value of Kc as well. All right. So Kc is temperature dependent. Remember that.
Yep.
Neither concentration, neither anything else can change the value of Kc, but temperature can change the value of Kc because Kc is temperature dependent. All right. At a specific temperature, Kc will remain constant. But if you change the temperature, Kc will change. But if you change the concentration, pressure, any other factor, then Kc value does not change. It remains the same as long as the temperature is same. All right. So this equilibrium was at 120 degrees Celsius. That's why it's asking you to calculate the value of Kc at 120 degrees Celsius because it's going to be constant at that value, temperature value. All right. So now Let's write the equation again. So we had two HI gases going into what? H2 and I2. 1 mole of both. This is the balancing of the equation. Now, should I make the table? Yes, you can. Let's make the table. So I need the initial moles, I need the used moles, and I need the equilibrium moles. What has been given in the question? Have I been given the initial moles of HI, H2, or I2? No. Have I been given the used moles? No. Have I been given the produced moles of the product? No. What have I been given in the question? It says the equilibrium mixture contains what? These many moles of HI, these many moles of H2 and I2. So which moles are these? If they're in the equilibrium mixture, these are the equilibrium moles, right? So I've been directly given the equilibrium moles. I just need to insert them in the Kc expression. So this is the type 2 question in which the equilibrium moles are directly given to you. So for HI, what are the equilibrium moles that I have? 1.47 mole per dm cube, and also in mole per dm cube. What are the moles of H2 and I2? 0.274 at equilibrium in the equilibrium mixture. 0.274 again mole per dm cube and mole per dm cube. So now can I just insert them in directly? Do I need to do any other calculations? My main objective even in the previous questions was to find these equilibrium moles of each of the species over here. Right? So now I have all of them. They've been directly given to me in the question. So I can just insert them in the Kc expression. I've already written the Kc expression. That would be right hand side, which is H2 and I2 to the power 1, and left hand side, which is Hi to the power 2. Right? So I just insert the values. To Kc would be, what's the right hand side? 0.274 mole per dm cube to the power 1 into 0.274 mole per dm cube into the power 1 divided by Hi, which is 1.47. So 1.47 mole per dm cube to the power 2. Now I solve for this. So Kc would be equal to what? Divided by
I'm getting 0.034.
0.034.
34.
And what would be the unit of Kc?
We have to find it.
Find that out. What would that be? We have two square brackets on the top and two square brackets on the bottom.
So no units.
No unit. All right.
Yep.
This was the second type of question, which is very easy compared to the first type of question. Right. Now we'll move on to the third type of question, in which you've already been given the Kc value and you have to find one of the equilibrium moles of either the reactants or the products. All right. So type 3 is Kc value is given in the question. Is given in question along with initial moles of reactant or product or both. It can be like that also. But the main thing is that Kc, you don't have to calculate Kc. It's already given in the question. So you have to go in reverse order. All right. So the question says a mixture containing 0.5 mole of carbon dioxide, 0.5 moles of H2, 0.20 moles of carbon monoxide, and 0.20 moles of H2O gas was placed in a 1 dm cube container or flask, for example, and allowed to reach equilibrium. and was allowed to reach equilibrium at 1200 kelvins. Now, temperature is important because if the temperature changes, Kc value changes, right? So it says that calculate the amount in moles, calculate the amount in moles of each substance present at equilibrium. All right. So you have the equation carbon dioxide plus H2 gas goes into carbon monoxide plus H2O. And you've been given the Kc value, that is Kc is equal to 1.44 at 1200 kelvins. So now we move on. Now, do I have to calculate the Kc value? No, it's already given in the question, right? What do I have to do? I have to calculate the moles of each substance at equilibrium, right? So I'll copy the equation. This is type 3, in which the Kc value is given. I'll copy the equation. I know the Kc value. What I'll do is I'll make the table again. The table makes everything so easy. So let's write initial, used, equilibrium. I need to get to equilibrium, right? Do I have the initial moles of everything? So the reaction is a mixture containing 0.5 moles of carbon dioxide, 0.5 moles of H2, 0.2 moles of carbon monoxide, and 0.2 moles of H2O was placed in a 1 dm cube container and allowed to reach equilibrium. What does that mean? Which are these moles that are mentioned above that if they were allowed to reach equilibrium after inserting into the dm cube container? Which moles should they be?
Initial?
They should be in the initial moles. So I've been given the initial moles of carbon dioxide and H2, that is 0.5. 0.5 moles, 0.5 moles, and I've also been given the initial moles of the product, which are 0.2 moles and 0.2 moles of water and 0.2 moles of carbon monoxide. All of these moles were placed in the container and then it was sealed and allowed to reach equilibrium. So I have the initial moles of these two, the 0.2 moles, 0.2 moles. So I've not been given any equilibrium moles, but I know the Kc value. What do I do next? So let's write the Kc expression if you're confused. Now, in order to find whatever missing moles are over here, I've been given the Kc value, so I'll write the Kc expression. So Kc would be carbon monoxide to the power 1, H2O to the power 1 right hand side, over left hand side, which is carbon dioxide to the power 1 and H2 to the power 1, right? And I know the Kc value, which is 1.44. That's not what I'm trying to find, not the Kc value. I'm trying to find the moles of each substance at equilibrium, right? So now what do I need? Whenever you're given the Kc value, you're expected to know some mathematical expressions. And that expression would be, if at equilibrium, let's find out the moles of, for example, the product at equilibrium. What would be the moles of product at equilibrium? Now we do know that these two will react and furthermore form carbon dioxide and H2O. These were already added to the solution, sorry, the container. But these two reactants have to react and form more of this, right?
Yep.
So the equilibrium amount would be larger than this, right? The initial moles. The equilibrium, at equilibrium, we'll find more moles than the initial mole, right? So what do? I know that the balancing of this equation is 1, 1, 1, 1, right? So I assume, because I have the Kc value, I assume that what if X moles were used from here? If X moles of carbon dioxide were used from here, what do you think? How many moles of H2 must be used from the reactant side? It's 1:1 between both these reactants. How many moles of H2 would be used? X
The
moles.
same.
Yep.
Yep.
And then if X moles of the reactant are being used, how many moles of the product will be formed? Again, it's 1:1 with the product also, right?
Yep.
So X moles of the product will be formed here and X moles would be formed here.
Yep.
Now do remember, if one of them were like 1:2, then 2X would be formed on the other side.
Yep.
All right. So now do I know the expressions at least of the moles that will be present at equilibrium? I know that at equilibrium, carbon dioxide would be 0.5 minus whatever the moles were removed from here, right? 0.5 minus X. What would be the moles of H2? They would also be 0.5 minus X. These were the moles, or it's the expression for the moles of H2 that will be left at equilibrium. The initial minus the used moles. What about carbon dioxide? How many moles would be present at equilibrium? That would be the initial moles plus these moles. So 0.2 plus X, right? And what about H2O? 0.2 plus X. So now I have the expressions at least of the moles of each substance present at equilibrium, right?
Yep.
And since I have the Kc value already, what can I do? I'll insert these moles over here and then I'll solve for X. All right.
Yep.
Now, before inserting them over here, I need to confirm, are all these moles in 1 dm cube? So it said in the question, they said in the question that these moles were placed in a 1 dm cube container. So are all these moles in 1 dm cube? The initial, the used, and
Yep.
then the final at equilibrium. All of them are in 1 dm cube. So all of them pass. Now I can insert them in the expression. So Kc was equal to right hand side over left hand side. I knew the Kc value at 1200 kelvins. I inserted that over here. Now I can write 1.44 would be equal to, what are the moles for carbon monoxide? There's 0.2 plus X. What are the moles for H2O? 0.2 plus X. And then what are the moles for carbon dioxide? That's 0.5 minus X and 0.5 minus X. Now can I solve further?
Yeah.
So
Yeah.
the easy way would be to do this. 1.44 is equal to, can I write 0.2 plus X whole square? When these two multiply, they become a square, right? This is the
Yeah.
same thing. So they become 0.2 plus X whole square, and the low one becomes 0.5 minus X whole square. Right? They're the same brackets.
Yep.
So now what I can do is I can take an under root on both sides, a square root on both sides. So I take a square root over here and I take a square root over here. The squares cancel out with the square root. And what's the square root of 1.44? Yep.
The square root of 1.44
Yep.
is 1.2.
So 1.2 is equal to 0.2 plus X divided by 0.5 minus X. Now just start making X the subject. So this bracket goes here and multiplies with 1.2. So 1.2 into 0.5 minus X is equal to 0.2 plus X. And now solve. So 1.2 into 0.5.
0.5 into 1.2.
Yep.
I'm getting 0.6.
So 0.6 and then 1.2 into minus X would be minus 1.2X is equal to 0.2 plus X. Now make X the subject, take the like terms on one side. So 0.6 minus 0.2 and this becomes X plus 1.2X, right? So this becomes 0.2 minus sorry, 0.6 minus 0.2 would be 0.4, and then x, 1x plus 1.2x would be 2.2x. That makes x 0.4 over 2.2. That is equal to x. What is the value of x? 0.4 over 2.2.
0.181.
0.181, right?
Yeah.
Now I have the value of x. What was I asked to calculate in the question? I was asked to calculate the amount in moles of each substance present at equilibrium. So I know the equilibrium expressions. Can I subtract the value of x that I now know from these? Can I put the value of x in these expressions to find out finally how many moles are present at equilibrium?
Yeah.
Yep. So for carbon dioxide, how many moles are present? That would be 0.5 minus 1 point. Are you sure it was 1.81? It was 0.181, right?
Yeah.
Yeah.
0.181.
So minus 0.181. How many moles of carbon dioxide were left at equilibrium? Yep. 0.5 minus
0.319.
0.319
319.
moles per dm cube. Right? And what about the other one? Same 0.319 moles per dm cube. And what about the other one? It's 0.2 plus 0.181.
I'm getting 0.381.
Yeah. So plus 0.181, that will be 0.381,
81.
right? Moles per dm cube, and the same for the next one also, because it's the same expression. 0.381 mole per dm cube.
Yep.
Now I know the equilibrium moles of all of the substances. All right.
Yep.
So when a Kc value is given, you'll be expected to find the equilibrium moles. In order to do that, you need to assume whatever moles are used, and due to those moles, how many moles will be formed. Make the equilibrium expressions. All right, equilibrium expressions for the moles of each reactant and product. Insert that in the equilibrium expression, equilibrium expression of Kc. You'll have the Kc value. You'll solve for x. When you find the value of x, then go back to the table and see what moles should be present for each substance. Are we clear?
Yep.
So that's all for Kc. The next equilibrium constant that we'll do is of Kp, right? So these are the few types of questions that will be asked from you. The first one would be like the initial moles of the reactants are given and the equilibrium moles are given. You're expected to form ratios and then find the equilibrium moles. And then after that, a very simple question in which all the equilibrium moles are already given in the question, right? So that is also very easy. But the third type of question in which Kc value is given in the question and initial moles are given, you're expected to make expressions in order to find the final moles and solve for x value, basically. All right. So these are the few types of questions for that.